day. This is a slight change to our original schedule. A student was supposed to present, but she couldn't make it, so her advisor is stepping in her place. Professor Brubach is a professor at Wellesley College in computer science, and he'll be rounding off our conference with a very interesting subject that everybody wants to know about: gerrymandering.
Yeah, this was voted by middle schoolers to be one of the more interesting subjects, right? I think. So that's good. And yeah, it's great to be the last speaker here, because I can kind of relate and be in conversation with the earlier talks. And I guess I have theoretically unlimited time. Is that correct? I can just talk. But yeah, so I'm not going to be talking about the work that I've been advising a current student on, because that's still sort of ongoing. But I'll talk about some work with a high schooler summer before last. So this is on essentially what happens when we start trying to measure and regulate gerrymandering in terms of voter incentives and things. But it'll be at a fairly high level, lots of proofs by example and picture. So should be pretty nice way to like finish off the day. So I'm going to give some quick background. See higher up in the chat. Got it. Sorry,
I'm sorry. That was answered to Stephanie's Stephanie's question. Sorry.
I'm used to teaching in this environment where I have to watch the chat. So I'll be giving a little quick background on gerrymandering. I know we've talked about it a little bit today, but just some specifics. And then I'm going to talk really on my work, which is looking at what happens when we start trying to measure and regulate gerrymandering using some of these recent tools for doing that, and then go into just some future work. And I have here the original gerrymandering political cartoon, which I think a lot of folks have seen, just to show the longevity of this problem, some recent work creating a font out of gerrymandered districts. So just my guiding example is going to be the US House of Representatives. This is a federal legislative body. And we all saw talks already talking about apportionment. So each state's given some number of representatives. My example here, we have Maryland with 8 representatives. States are divided into districts, and each district's going to choose a representative by a plurality vote. Although for the purpose of this talk, you can just think of a majority vote, because we're mostly going to be talking about two-party situations. And we have this concept of redistricting every 10 years or so after a census, like right now. We need to redraw district maps in order to keep population balanced as people move around, and also handle apportionment changes, right? So if a state gains or loses representatives. And in this case, we think this is where gerrymandering arises, right? So we want to draw district maps in some way to manipulate the outcome of elections. And you can think of partisan gerrymandering for political parties, racial gerrymandering, where you're benefiting or disenfranchising a racial group, incumbent gerrymandering. And these all interact with each other. They're not really separable, but we are going to try to focus just on partisan gerrymandering for today, although in the questions we can talk about how they intersect. And I just have my home state of Maryland here with, this is the 2013 redistrict. So the original map was on the left, and on the right is what happened in 2013. So it went from 2 Republican representatives down to 1, which if you know the political geography of Maryland, you'll see how that happened. That light blue district at the top was a Republican district and then changed in the second map to a Democratic district. So just one example of gerrymandering. Another one, North Carolina, which was grouped together with Maryland in a recent Supreme Court case. So I think this just really illustrates, I think, the extreme situation with gerrymandering. So North Carolina has 13 representatives. And if you look at the 2016 election and percentages of votes just based on some statewide election like Senate or president, you can see that it's roughly 50-50, slightly leaning Republican. And we saw that again in 2020. And yet it's electing 3 Democrats and 10 Republicans as its representatives. And you can redraw these maps actually to elect 10 Democrats and 3 Republicans, or anything in between. So this is a pretty dramatic, this is like a 14 vote swing just in how one state is drawing its districts with only 13 representatives. which is more than the difference in power in the US House of Representatives right now, right? So the Democratic Party and the Republican Party in the US House right now are about 7 seats apart. And so, you know, really just how we draw these maps can swing the whole balance of power in this enormous body, federally, you know, when you're just, even though one state's doing it. And, you know, some of the intersection with my work. So I come from a background in theoretical computer science. And so now computers are increasingly being used to draw gerrymandered maps and also being used to address the problem of gerrymandering. And so that's partly where I come in here. So, and I'll just add, so state governments are the ones that are drawing these maps in most cases. They're the ones that do it. So just a quick, simple example just to illustrate how gerrymandering works. I don't think we've seen, well, we've seen a little bit of these types of pictures today, but I don't think we've seen these exact ones. So this just looks at a 5x5 grid of 25 people. Let's say we have 10 of them are voting for the blue party, 15 are voting for the red party. And you want to divide this into 5 districts of 5 people, or you can think of these as counties in some square state, if you want to make it a little more realistic. And these have to be contiguous. So there are 4,006 possible ways to do this on a 5x5 grid. We'll see later why I know that. And they come up with different results, right? As we saw with the real maps. So you could have this map on the left that is more or less proportional, 2 blue, 3 red, which kind of represents the proportions in the population of each voters. You have this map in the middle, which completely disenfranchises the blue group and gives 5 seats to the red party. And then this other map, which gives 3 seats to the blue party and 2 to the red, even though the red is in the minority, right? And these are examples of our basic techniques of gerrymandering, which are fracturing or packing. Sometimes they call it cracking and packing. This is where you take, in the case of the left here, a bunch of like-minded voters and you break them up into different districts so that they can't vote together, so that their votes are sort of watered down. Or you can take, on the right side, you can pack them together into the same district so that their votes are essentially wasted, right? In these districts, they only need 3 votes to win, but you know, this district in the purple outline here has 5 votes, right? So these extra 2 votes are kind of wasted. And if you see me glancing to the left here, it's because I have a second monitor with all your faces, so I can kind of sort of feel like I'm in a room full of people just a little bit, which I miss so much. And so with that out of the way, let's look at an even simpler model, right? So we're going to go down from the 5x5 grid to an even simpler 3x3 grid. And that's all we're going to need to show some of the work that I'm talking about today. So for those of you that are, I don't know, working with you know, high schoolers or middle schoolers, right? You really can do a lot with these very simple examples that don't require a lot of, you know, hardcore data science or scalability. So here we have this 3x3 grid. Each voter prefers one party. So we have these blue triangles and red squares for the blue party or the red party. And a map is just going to partition this into 3 districts of 3 voters each. And they have to be orthogonally adjacent, so they have to be contiguous. And again, you can imagine these as counties instead of voters if you want to make it more realistic. We'll come back to realism at the end. And so each district is going to elect 1 representative by a majority vote. So the first question I like to pose is how many of these district maps are possible? We saw with a 5x5 grid that there's about 4,000 ways you can do this. Noting that we're going to count this first one and this fourth one here as 2 different maps because they certainly function differently in terms of the way that people are handled here, the different voter configurations. And so the answer, if you thought about this for a little while, I'd love to be able to just poll everybody. And the idea would be if we could all place bets on it. But the answer is 10 maps. So you can get 10 possible maps out of just this 3x3 grid, which is nice because it lets us explore the space of all possible district maps in this example. So if we look at these 10 maps and we think about, you know, how many seats each party is going to win in each map, something we might notice fairly quickly, if you were to go and sort of calculate each of them, is that the first map is the only one to award 3 representatives to the red party. And so, most of us, if we're looking at this, are thinking, okay, that's probably not the map we want. We want a map that's more proportional, or more similar to the other maps in some way. There's a lot of different values we might have about what a fair districting is or looks like, but most of us would kind of want to rule out that first map. And this has been like the major challenge that only recently really has been addressed, was like, how do we think about this? How do we think of a way to really like mathematically rule out certain maps? And so we think, what's a rule here that would prevent gerrymandering? And the simple rule that I'm going to state, because simple is important when you're talking about, actually making laws or, things involving voters, right? Outside the world of just math. So the simple rule would be, if a map awarding X seats to one party is rare, let's ban that rare map. And I'm going to call this the banning outlier maps rule. Okay, great. How do we know that a map is rare? It was easy in our past example with only 10 maps, but with a larger situation, maybe we just randomly sample a bunch of maps, right? We can't look at all possible maps of a state, all possible ways to district a state, but maybe we randomly sample. Okay, good. How do we sample uniformly? We want to look at the space of all possible district maps. So probably a lot of you are like, no, that's not going to work. And yeah, we can't really do that. We can't just sample uniformly from all possible maps, but it turns out we can come close enough, at least close enough for a lot of legal definitions. So there's been this recent work using these Markov chain Monte Carlo approaches, which for a lot of you mathematicians, I'm not going to talk a lot about this, but it's really cool stuff. Basically taking random walks through the space of possible maps with some restrictions on what a map can be, and using that to generate say 2,000, 20,000 random maps, and comparing a specific map to that set of maps, right? And also, how do we define rare, right? That's easy. Pick an arbitrary threshold like 1%. That's fine. Actually, I think we use 2%. Yeah, we use 2% in our paper, but you could use 1%. And then this has overturned maps in states like North Carolina and Pennsylvania, which we talked about earlier. So it's worked in state courts. It wasn't successful in the Supreme Court case, although there's a lot of other factors there. But as a measure, it's the measure that has finally been somewhat adopted. There's been a lot of other attempts at measures like efficiency gap and things like that haven't really worked out. And this is the one that I think has had the most success in being used as an actual measure of, is a map gerrymander. Okay, so there we are. We've determined that our first map is an outlier, 1 out of 10. That's the closest, that's not 1%. That's the best we can do in this example. So we've determined that that's an outlier. We're going to ban maps that award 3 representatives to red. Are we done? And so this is where my work starts. And I bring this up, especially when I'm talking with computer scientists, right? We think about this now in terms of algorithmic game theory and social choice. So we have this sort of algorithm for, drawing a bunch of random maps and determining that some map is an outlier and we should ban it. But how did we actually do this? So this is if you've tuned out a little bit, because I've been talking about stuff you already know about gerrymandering, here's the point to tune back in. So the idea is that when we took a big random sample of maps and evaluated, which party would get some number of seats on each map, we used past voting data. So we used like data from a previous Senate election or something like that to simulate who would win a number of seats in a given map. And if we're using past voting data, then your vote does more than just affect a single election, right? Your vote is going to be used in this measure of gerrymandering. And so this now adds in a factor of strategic voting, which is unavoidable with more than 2 parties. We saw some discussion of this earlier. I don't think we actually got to Gibbard-Satterthwaite in any of the talks, but we talked about Arrow's theorem and we got close to it. And typically we think of this not being incentivized with two parties, right? If there's two parties, you're typically incentivized to just vote for the one that you prefer. But we'll show that actually, in this case, we can show a model where you're not necessarily incentivized to do that because your vote is potentially affecting the way future maps are drawn and affecting multiple elections. And so this is joint work with my PhD advisor at Maryland, Arvind Srinivasan, and Sean Zhao, who was a high schooler at the time, but is now an undergrad at UC Berkeley. So how does this game work? So we set up a game where we start with an arbitrary map, or you can think of one chosen by a party, but for simplicity, let's say an arbitrary map. Then we have a round where we vote and award seats to each party. Then we have another round where we draw a new map, and we have this banning outliers restriction where we can't draw an outlier map based on, looking at the previous votes. And then we vote and award seats again, and the goal for each party is to win as many seats as possible over these two voting rounds. So what does this look like? Let's say we just chose this map for 2 rounds. So in this case, in the first round, red wins 2 seats. We can see that, red wins this district on the left, and this lower right corner, red clearly wins. And let's say we just stuck with this map. In the second round, we would vote again. Red would win 2 seats and win 4 seats total. But what if one of the voters in the red party decides to lie and vote strategically, right? So now let's say this lower middle voter decides to cast a blue vote in the first election. This doesn't affect the number of seats won by the red party in the first election. So red still wins this district. But it changes what the maps look like. So in round 3, when we're redrawing the maps, this map, which was our upper left corner map from our slide of all 10 maps, now looks like a valid map, right? It looks like this center column here will elect 1 blue representative, and these 2 side columns will each elect a red representative. Now we have to be a little careful here because we have to show that electing 2 red representatives is still not an outlier in this new configuration, right? Because now we have a new configuration of voters that has what we think are 4 blue voters, but take my word for it that this is not an outlier by our previous definition on these small maps, right? So now this looks like a valid map. So now the red party is allowed to draw this map in round 3, and then in round 4, of course, they go back to voting their true preferences, and they win 3 seats for 5 total. So that's a better number of seats for the red party. And now you might be asking, okay, so we talked about how the red party can change their vote, right? And if you're a game theorist, you're thinking, okay, well, what about the blue party? The blue party has to respond to this. And it turns out there's pure strategies in this case for all of these maps. So no matter what map you start with, in this just little 3x3 grid example, you can always find a strategy for the red party to vote strategically, such that there's really nothing that the blue party can do. So there's no way that the blue party can, counter this method of the red party getting 5 seats. And if you look down here, several of these at the bottom, you do have to flip 2 red voters here. And that is to account for the possibility of the blue party voting strategically. So in all 3 of these, the blue party could flip that center voter without losing that district in the first round of voting. And so that's why you need to flip these 2 votes. So this inspires for us kind of a general strategy or heuristic that works for larger instances. So we can look at this. This is the way we sort of thought about it. If you were trying to cheat in this way, you need some kind of strategic voter for your party, right? So down at the bottom, you need somebody in your party who's going to vote strategically. And crucially, that voter can't cause you to lose a district, right? Or else you'd have to gain more back. But in the simplest case, you probably don't want to lose a district by that person voting strategically. So in this case here, we see that this person can flip and they don't lose this district because there's 2 other red voters. And then you need this other person who we're going to call kind of a forced accomplice, who's going to help make this look like a valid map, right? So in this new map that we draw, where we have 1 fake blue voter and 1 real blue voter, that makes it look like blue wins a seat in this center column. This blue voter is almost being like forced to participate in this scheme to trick the system. And the reason for that is that they can't flip their vote in the other map without changing the outcome of the first election, right? So in this first map, if this blue voter were to flip to red, their district would go red, and they would lose a seat there, and then red's already won. So extending this out a little bit farther, we looked at 5x5 grids, which is a little bit more realistic, but still gives us the ability to not even worry about this whole random sampling thing, because we can actually look at all 4,006 possible maps, which interestingly, when we did this, I couldn't find online, some data that actually had these maps already made for me. So I had to go write some code to actually generate all of these maps, which was an interesting little programming puzzle that I encourage you to try. All of these ways to tile a space with polyominoes of size 5. And we were able to study all 3.2 million ways to place 10 blue voters and 15 red voters. So this 40-60 split. So we looked at all possible ways to arrange voters with this breakdown in a 5x5 grid, and all possible maps that you could use with those voters. And so for all possible ways of all these 3.2 million possible ways, we found a pure strategy about half the time using this heuristic. And the reason why it was only half the time was because half the time, a map that gave 5 seats, all 5 seats to the red voters, turned out to be not an outlier. So half the time in these voter configurations, the configurations were such that they favored the red party enough that just giving the red party all of the seats wasn't really an outlier. But in the other half of maps, giving the red party 5 seats was an outlier, but by our definition of occurring in only less than 2% of maps. And we were able to find a pure strategy that basically you start with a map that only awards 4 seats to the red party, you vote strategically, and then you can draw a map that gives 5 seats to the red party. We further extended this to real North Carolina data, and here we had to make an assumption that the other party doesn't cheat. So I don't know how to find like a pure strategy in this case, but here for our heuristic, we assume that maybe it's like a sneak attack or something. The only one party is voting strategically. So here we looked at the old North Carolina maps that were used in 2016 that were seen as gerrymandered, where 3 Democrats and 10 Republican seats were awarded. And we compared that to this map known as the Judges map, which was a map that was drawn by a bipartisan commission of judges that awarded 4 seats to the Democrats under that same voting data, and 9 seats to the Republicans, which is not an outlier map. Even though it's among the possible maps that favors Republicans, it's not an outlier. And using, we show that you could move from, essentially move from the Judges map. If you started with the Judges map, which is not an outlier, you could find a set of voters to vote strategically. And assuming the other party doesn't respond, you could make that bad map look good again, and be seen as a valid map the next time you were drawing districts. So just to wrap up here, I know we're running out of time. So we also addressed some, I'll skip through this really quick, some questions in the Supreme Court case. Is banning outliers just a proportionality test? So I want to say emphatically no. Contrary to what some Supreme Court justices believe, you can actually find situations where the most proportional map is itself an outlier and would be banned by this rule. So I think that invalidates it from being a proportionality test. There's also this question of, if you do a bunch of random maps, and if a person is usually in a district where their party wins. Do they have a right to be in such a district? And unfortunately, it's impossible to guarantee that for every voter at the same time. There's no single map that satisfies that criteria for every voter that is in a district where their party wins in the majority of random maps. And we've introduced some other notions of pairwise fairness, and I just want to finish up real quick. I think I might be a little over time. With just some quick lessons from algorithmic fairness, where I've been working a lot in the past couple of years. One, I want to say beware of the unbiased algorithm. I've seen a lot of algorithmic approaches to, hey, we'll draw districts with computers and they won't be biased. That's like never true. Anytime somebody says an algorithm is not biased, it really means that they don't know that the algorithm is biased. And so, for instance, like just excluding partisan information when you're drawing the districts, that's like a classic thing that's come up in algorithmic fairness in terms of other applications like hiring and criminal justice applications. You can't just remove the sensitive features because they're redundantly encoded in other features usually. We should look at proxies for fairness. So ensuring fairness to political parties is not necessarily the same as ensuring fairness to voters. And also anticipating downstream effects. So, looking at how these things affect voter incentives. All right, so I'll wrap up. Thank you. And I'm open to any questions.
Thank you very much, Brian. That was a wonderful talk where gerrymandering is fascinating. Are there any questions for Brian? So while you guys think of a question, I just want to, say something completely irrelevant, and that is, something that I heard, an interesting fact about math that made me that I thought about while Brian was talking about, tiling like, a space. And here's an interesting fact. Okay, so for those of you who know what a determinant is, a determinant of an n by n matrix has n factorial terms, half of which get a plus sign and half of which gets a minus sign. And there's another property that you can compute of a matrix called the permanent, where it's exactly the same as a determinant, except all the terms are plus. There are no minus terms. So it turns out that the number of ways that you can tile a grid using dominoes, okay, can be computed using the permanent and the determinant. So that is a very, very wacky linear algebra fact that seems completely, impossible. Okay, so now you can have some time to think about some questions for Brian. Anybody?
Yeah, I can. Yeah, that's funny. I mean, I could talk more about all of the things that I could find online about tiling spaces that were not what I wanted to find when I was looking for this, and then eventually resigning to have to draw it myself. Which I think maybe Moon Duchin's group has them up now. I don't know, but I didn't find them when I was looking for them. But sorry.
Well, I'm interested to know how this plays into or how it interacts with with the Pennsylvania criterion, which counts political subunits, and this sounds related to the talk about simplices too. So criteria that take into account existing political subdivisions of the state. So the Pennsylvania criterion says take the map and ask, when you look at your set of districts, how many counties are split, how many wards are split, how many towns are split. Mm-hmm.
So yeah, the interesting thing there is all of these states have these rules like that, but they have, or many states have some kind of rules like that, but they have rules that are essentially conflicting. And so that kind of gives them, I think, a little bit of a blank check. This is my interpretation a little bit I'm not a political scientist, I'm a computer scientist, but it kind of gives them a blank check to, violate them. Because, right, you want to keep the population in the districts balanced, right? And then at the same time, you want to avoid breaking up these communities, right? Breaking up counties and things like that. And you already can't necessarily do both of those things. So, once you can't do those things, then I think the floodgates.
Well, I mean, in practice, though, I mean, in Pennsylvania, at least, the rule did have real effect in Holt v. Commonwealth, because, you know, without perfectly obeying any one of the rules, they said, look, you know, you're splitting way too many districts, go back and draw it again.
Yeah.
So,
Yeah,
and I guess my bigger question is when I look at purely mathematical redistricting algorithms like the ones you describe, what comes to my mind immediately is, you know, but some groups of voters are more grouped than others, that there are existing political units, and that to ignore them, you know, maybe is ignoring something important.
So yeah, a lot of the algorithmic techniques do take that into account, both the techniques that are used to draw districts computationally, or if they're in a more theoretical conference, they just say, hey, our method could take this into account. But you know, also the methods that are randomly sampling these maps are taking stuff like that into account. They all have ways that you can add in different criteria and restrictions like that. But I don't know, am I supposed to call it? Ismar, your hand is up. Am I supposed to be calling on people?
Sure, Ismar, yeah.
Yeah, actually, there was a question in the chat before I raised my hand. Sarah is asking about the efficiency gap. Why is the efficiency gap standard not considered useful?
Yeah, so I mean, I think my short answer is that it was somewhat unsuccessful in some legal challenges. I think there's other criticisms of it. I'm blanking on the name. Moon Duchin and someone else had a really nice paper sort of analyzing the efficiency gap a few years back.
Mira Bernstein, who was actually at Wellesley for a while.
Yeah. Moon and Mira had this nice paper. I can't think of the name of the efficient, but that talks about, I think that's formula goes to court. Yes, thank you, chat. So I mean, in terms of like critiquing the efficiency gap, I think that's like the best place to look. I mean, the fact that it sort of prioritizes like weird 75-25 splits and other things. There's a lot of weird things about it. I think it was like a really lovely idea, this concept of wasted votes, and it was so simple, which is important and really useful in practice. So I think it was like a great idea, but I think ultimately it hasn't really been successful, and it has some issues mathematically.
Ismar, you have a final question?
I have a quick question. So is the conjecture, maybe you said this, and I'm sorry if I didn't pick up on it. Is the conjecture that there's always a pure strategy for outliers? And does that depend on how you define an outlier, what percentage you assign to define it?
Yeah, no, I don't know that there's always a pure strategy. I mean, we were only able to show that, you know, there exists a situation where, you know, we could incentivize voters to vote strategically. And we only had basically a heuristic to find these strategies.
But your 5x5 example seemed like it had pure strategy every time. For half, you said half the time, but those were the half that were the outlier, right?
Yeah, so there we found, for all of the ones where there were, I think basically all of the ones where the 5-seat map was an outlier, we were able to find a strategy, but it was a heuristic process for finding that strategy. We didn't have any proof that you can do that. And the analysis to show that it's a pure strategy is also kind of prohibitive to anything larger than that. So it's kind of open, getting some, I think, harder, more formal statements there.
Thanks.
So we made it to the end. Let me just conclude with some final words. You know, as